Do you want to remake the way we make things? If your answer is yes, you are at the right place. Welcome, everyone. My name is Mohammed Sajid. I'm a solutions architect at AWS. With me, I have Markus Ulmeforsch, Director Data and Machine Learning Platforms at Northvolt. He's here to talk about how Europe's first homegrown gigafactory, Northvolt, is producing sustainable batteries in their connected factory. You will meet Markus very soon. Both me and Markus are from Stockholm, Sweden. All right, I have a habit of keeping my browser tabs open. There is a special term for this called tab sunduku. Sunduku is a Japanese word for impulsively acquiring and piling up books without ever intending to read them. So raise your hands if your browser looks like this on a daily basis. Welcome to the club. But we can't keep opening new tabs forever. Anything we can't keep doing forever is obviously not sustainable. So you're not here to listen to my unsustainable habits. You are here attending a level 300 breakout session where you will learn how manufacturing customers are leveraging AWS in their sustainability journey. Let me ask you a question. Raise your hand if you are responsible for sustainability at your company. I expected every one of you to raise your hands. You know why? Just like security, sustainability is everyone's responsibility. Let's look at the agenda. Today, you will learn how manufacturers can use data to become more sustainable. What are some of the modern technologies you can use to optimize factory operations? I will also show you a short demo of AWS IoT TwinMaker. And obviously, Markus from Northvolt will share his or their experience of using AWS to operate connected factory. In the end, I will leave you with some call to actions and learning resources. So are you ready? Show some excitement. Are you ready?
Yeah.
Yes. Do you know what is the average temperature of the Earth? Raise your hands. Today, the global average temperature is about 15 degrees Celsius and increasing faster than ever. The 20 warmest years on record have been in the past 20 years. So research says average global temperature may rise by 3 to 5 degrees by the end of this century, until 2100. Scientists also tell us that we have a limited window to make unprecedented headway in order to limit global warming to 1.5 degrees Celsius by year 2050. And why this is important? This is important to avoid serious climate issues, including heat waves, floods, harsh weather, and all those possible things, including the possibility of extinction of several living species. But my question is, why Earth's temperature is increasing? A lot of global warming is happening due to the greenhouse gases generated by human activities. So what are the greenhouse gases? Greenhouse gases trap heat in Earth's atmosphere that in return makes the planet much hotter. There are many different greenhouse gases, including carbon dioxide, methane, nitrous oxide, and many more. The collective term greenhouse gases also goes by the more scientific name called carbon dioxide equivalent. And this is the 50 billion tons or 50 gigatons that we are dealing with every year. Out of this 50 gigatons, how much do you think is contributed by the manufacturing sector? Roughly 21% or approximately 10 gigatons every year. Let me put this into perspective. So 1 gigaton is roughly 200 million elephants if stacked vertically on top of each other would stretch all the way from Earth to the moon. Hence, the 10 gigaton is 10 stacks of elephants stretching from the Earth to the moon. And we don't have to be alive and wait until the end of the century to see the consequences of the climate change. For example, this year, around 33 million people, including 16 million children, have been impacted in my native country, Pakistan, by the devastating flood caused by climate change. So 33 million people, they are more people than the combined population of all the Nordic countries, and these are more people than the population of Texas state that were impacted. So the picture you see here, this is the before the floods satellite image where you can see Pakistan's largest freshwater lake called Manchar. After the floods, there is no sign of fresh water, just the stagnant, contaminated water, which is just a breeding ground, acting as a breeding ground for mosquitoes. As I said, we don't have to wait. Future is already here. It's just not evenly distributed. And obviously, manufacturing has an outsized impact on the environment. According to the IEA, industrial activity in the year 2021 was directly responsible for emitting 9.4 gigatons of CO2. And by the way, this does not include the indirect emissions from electricity used for industrial processes. According to the same report, fossil fuels remain the dominant source of energy for industry. The manufacturing industry contributes significantly to greenhouse gases and manufacturers use a lot of water and energy. That's the reason, manufacturings are also the most targeted industry in sense of sustainability. And obviously, we have more opportunity to improve. But there are trends in manufacturing that can help reduce negative climate impact. We are experiencing the fourth industrial revolution live. The first revolution brought mechanical innovations like steam engine, cotton spinning, and railroads. Second brought the mass production through assembly lines and electrification. Third, which is my favorite, by the way, brought computers and the internet. The fourth revolution is bringing physical, digital, and biological systems together. And Industry 4.0 is reinventing the entire manufacturing process around the power of the data and cloud. Manufacturing is one of the largest producers of the data that customers can use to improve insights to become more sustainable and more profitable. But what is the challenge? The biggest challenge within the plant floor for a majority of manufacturers is visibility into operational technology data from machines and basic control systems. So let's see how industries have been using data and where they are going now. Are you aware of the ISA 95 framework? Raise your hands. So ISA 95 is the international standard for the integration of enterprise and control systems, which is a traditional model before the cloud era. Traditionally, manufacturing technology has been split into operational versus information technology, where operational technology, or OT, has focused on the sensors and softwares that monitor and control the manufacturing process. And information technology, IT, has provided the separate function of data processing and analytics. So ISA 95 model consists of field and control and management levels. The field and control levels consist of basic control systems like supervisory control and data acquisition, or SCADA, and programmable logic controller and distributed control systems. The management level consists of business logistics and manufacturing operations, operating systems like manufacturing execution system, MES, product lifecycle management, and ERPs. So historically, this monolithic model was good before the cloud and edge computing era. It created data silos, and integration was a huge challenge due to over 300 commercial industrial communication protocols. With the cloud and open platform communication, unified architecture, or OPC UA, the traditional model has evolved significantly, and IT-OT divide is minimized. With IT-OT convergence, operational technology environments are leveraging more IT solutions in the cloud to improve productivity and efficiency of production operations. But what about today? Today, in the time of physical meets digital, with increased computational power and connectivity, IT-OT border is invisible, and industries are adopting hybrid edge cloud architectures. And why they do this? To run latency-critical systems on the edge close to the factory floor where all the action happens, and send volumes of data to the cloud for analytics, BI, and machine learning operations. So what makes sustainable manufacturing a possibility? Modern technologies. So there are a lot of ways manufacturing customers can use data to become more sustainable and more profitable. I will share just a few examples with you. You can lower electricity, heating, and cooling needs of a building by occupancy detection, better insulation and ventilation systems. Similarly, upgrading to smart LED lighting in buildings and elevators can help reduce your energy usage by up to 75%. By the way, are you aware of that AWS is going to be water positive by year 2030? And what does it mean? It means AWS will be providing more water to the environment than it consumes for its own operations. So just like humans, machines can now tell you what they are feeling right now. Are they feeling good or bad? So according to McKinsey, predictive maintenance can increase production line availability by 5 to 15% and reduce maintenance costs by 18 to 25%. With Amazon Monitron, you can monitor and detect abnormal machine behavior and enable predictive maintenance. Monitron is like a smartwatch for machine. You stick it to a machine and you start getting temperature and vibration data for that machine. So raise your hand if you know the average lifespan of a factory equipment or an asset. Roughly 18 to 22 years. And with predictive maintenance, you can improve overall equipment efficiency, OEE, and lifespan of a machine even further, more than even 22 years. So digitization enhances shop floor safety as well. Factory buildings can use temperature, air quality, and occupancy data to improve staff safety and comfort. As I said in the beginning, data is the key enabler for sustainable manufacturing. And today it is possible to collect volume and variety of data using industrial IoT. But collecting data is easy. Realizing value from data is challenging. According to the World Economic Forum, effective use of data in manufacturing can make businesses more sustainable and more profitable. That said, only 39% of executives they surveyed said they were able to scale a use case outside of a single product's production process. Similarly, Forbes recently surveyed more than 400 manufacturing executives in United States and UK, United Kingdom. Only 44% of respondents said recent modernization efforts have provided them with actionable data, while 19% have not harnessed any data insight. I'm going to focus on just a few AWS services that fast-track adding digitization to your factory, and Northvolt will explain their architecture that incorporates even more aspects. And cloud is the catalyst for achieving these Industry 4.0 capabilities. AWS IoT and Edge services allows you to ingest industrial IoT data to build smart factory capabilities. Similarly, industrial customers can harness virtually unlimited compute, AI/ML, and analytics capabilities using AWS Cloud. So one way to gain insights from the data stranded between the four walls of a factory is to extend cloud capabilities to the edge. That is bringing cloud to the edge. So today, industrial companies want to ingest, store, and analyze IoT data closer to the point where data is generated, where all the action happens, which is the factory floor. So why they want to do that? To enable predictive maintenance, improve overall equipment efficiency, and enhance worker safety, and even more things. So industrial customers can greatly benefit from the edge to keep data and compute local to the low latency environment. They might have intermittent connectivity and adherence to regulatory guidelines. And by the way, transferring huge volume of data to the cloud is also economically not very beneficial. So here is a subset of the purpose-built AWS services to support industrial customers to build smart factory capabilities. Inside the factory, AWS Edge services communicate with the industrial equipment, collecting and analyzing data, sending commands, and running local applications. Data sources at the edge may include SCADA systems, third-party protocol converters, data historians, and even web APIs. You can ingest data directly using AWS Lambda or AWS IoT Greengrass, or use AWS IoT Sitewise for data that requires asset modeling. Once your data is in the cloud, you can use Amazon S3 as a data lake to store volume and variety of factory operational data. So you can use multiple AWS services to enrich and analyze the data. For instance, users can apply data science tools such as Amazon SageMaker to provide insights from machinery across the shop floor. So let's go one step further. With the digital twin, you can improve the physical twin through rich data insights and leverage infinite opportunities to simulate proactive and reactive changes. So digital twin is a complex domain. If we ask 10 people to define what is a digital twin, we might get 11 different definitions. So let's see how AWS defines it. Simply put, a digital twin is a living digital representation of a physical system that mimics the looks, behavior, and state of the physical system to drive business outcomes. For example, imagine a digital twin of a smart home with interconnected sensors and IoT devices collecting data about physical items in the home, allowing you to visualize and control security access, temperature, lighting, and other home appliances remotely. Why do you do this? You do this to monitor and reduce energy and water consumption and increase occupants' health, safety, and comfort. But digital twin building is a complex, time-consuming, and a costly operation, and it requires specialized developer skills that not every customer has. Let me go back to the digital twin of a home example. In order to have a proper digital twin, you need time series IoT data from sensors, video data from camera feeds, and data from a variety of other home appliances, like dishwashers, washing machines, and what have you. You would even need 3D visualization or 3D drawings of your home in order to visualize and operate things in their natural context. And what happens when you replace your old faulty machine with the new one? How do you update the 3D model and bring new data into the system? Similarly, what about when you plan to change all your light bulbs? Now imagine the magnitude of work that will go into building a digital twin of a factory. With AWS IoT TwinMaker, you can easily get started with creating digital twins of real-world systems, such as buildings, factories, industrial equipment, and production lines, and use them in web applications that operators can use to monitor and improve operations. So IoT TwinMaker gives you the ability to use existing data from multiple sources, so you do not have to bring data to the IoT TwinMaker. So IoT TwinMaker connectors go to the data and fetch it. So you can also create virtual representation of any physical environment and combine existing 3D models with real-world data. So you can now harness digital twins to create a holistic view of your operations with less efforts. So how does digital twin work? Let me explain you a little bit. So AWS IoT TwinMaker provides you a workspace, which is a top-level container for your digital twin application. It also serves as a security boundary to manage access to the application and its resources. With IoT TwinMaker, you get tools to model your system by using an entity component model knowledge graph. This entity component model contains entities, components, and relationships between these entities and components. So what are the entities? So entities are digital representations of the element in a digital twin. These elements can be a piece of physical equipment, a concept, or even a process. And obviously, these entities have components associated with them. These components provide data and context for the associated entity with the help of connectors. And you can have a lot of different types of connectors. You can use built-in connectors or create your own connectors if required. Similarly, you can use existing 3D models and drawings combined with entities and components to augment a three-dimensional representation of your digital twin and then view it in Grafana dashboard. Let's see TwinMaker in action. So I will switch to the laptop where I have already recorded a demo. So here you see I'm logged into the AWS console and I have already configured a couple of workspaces in the IoT TwinMaker. So let me show you one of the demos called Cookie Factory that is available in the GitHub for you that you can use and deploy within your account. So let's start with this demo. So as you can see, I have already created a workspace called Cookie Factory. In that workspace, there are multiple scenes. So what is a scene? Scene, you can represent a room in your home or a factory floor as a scene. Including, you can have, for example, if you have a building and you're representing a building as a digital twin, you can represent an entire floor as a scene. And obviously, you can have as many scenes as you want to create a digital twin. And there are obviously a lot of entities pre-created for this demo that you can use, and entities could have a hierarchy. So you can have parent-child entities. And obviously, I have imported a lot of resources 3D models and resources that we will use to build this digital twin. So what kind of 3D models IoT TwinMaker supports? IoT TwinMaker supports GLTF format and other binary formats. So GLTF is a graphic language transmission format, which is very web-friendly. All right, so let's open the Cookie Factory scene, and you can see that the entire factory floor is represented in a 3D environment, and you can see a lot of cookie lines, mixers, and a lot of things happening inside the factory. All right, and you can see these 3D diagrams are connected with the help of tags and a lot of other information. So components and tags. So you can call tag as an anchor as well. That's how you connect digital twin 3D model with its data. All right, so you can also see there is an hierarchy between different entities. Similarly, you can actually run queries for your digital twin, IoT TwinMaker digital twins. For example, if you have a lot of entities and you have a lot of hierarchy within the entity component, then you can use Particle, which is a SQL-like query language, to query your entities and components. And if your entities and components have relationships, you can even represent them visually, so within the visual graph. So obviously, in this demo, we have a lot of information. And since I selected mixers, so you can see a lot of mixers coming in. All right, but how does a factory operator sees all that? Factory operator is not logged into the IoT TwinMaker console, and they are not looking at the console all the time. So they use the Grafana dashboard. So developers can build Grafana application for the factory operators. For example, you can see in this Grafana dashboard, there are already a lot of panels here. You can even bring in video feed, Kinesis video, through Kinesis video stream for your factory operator so that they can see where action is happening, what's going on. They can actually help their staff become more safe while working in the factory environment. So I will remove this video feed so that I can actually show you the same 3D model that we have seen earlier in this view. And here you can see one of the mixer at the bottom is turning red. And there could be a problem going on with this mixer. And the factory operator can easily tell where this mixer exists within this factory floor and how they can actually use this information to help people around this mixer so that they are aware of the problem and they can actually be more safe rather than being in danger. So that is the beauty of viewing it in a digital twin way, together with the 3D graphics. So, but now we have a challenge. So challenge is this Cookie Factory is running on the fossil fuel energy. They want to improve, they want to have a better energy mix, and they want to implement windmills, wind farm. And as a developer, our job is to actually make this happen. So what we will do, we will create a digital twin of a windmill very quickly. So I have already created a workspace called wind farm, and you can see there is no scene and no entity created yet. So what I will do, I will quickly create an entity, give it a relevant name, for example, windmill 001. And after creating the entity, I will associate a component with this entity. And this component is actually getting data from IoT site-wise. So that's why I'm using IoT site-wise connector. And I have already configured an asset model within the IoT site-wise. So what I will do, I will just select that model name and the asset. But what does this asset include? So this is an asset of a windmill. So it is actually capturing the speed of the wind. Raise your hand if you know the name of the device used for measuring wind speed. So the name of the device is anemometer. All right, so I will click Add Component, and this entity is created together with the component. So let me show you how does it look like, how does that model look like in this IoT Sitewise very quickly. So I will open Sitewise within the console in new window. Now you know what kind of tabs I was talking about. Everything is in the new tabs. So as you can see, the model name is wind farm, and within this wind farm model, I have associated asset, which is windmill 001, and what kind of measurements I am capturing is the speed, which is in RPM, and this is the mock data that I am getting from one of the Cloud9 instances behind the scene. I actually went ahead and created the IoT Sitewise monitor, and through the portal, you can see there are a lot of you can create dashboards. So I have already created a dashboard just to see how does it look like for the factory operators, plant operators, like how they can see, how they can use Sitewise monitor to track what's going on within the factory. All right, so let's go back, and now we have the entity. I have already imported few 3D assets. So let's create the scene now. So I will use create scene option here, and obviously give scene a relevant name. So scene name is wind farm. And in this modeling window, I will add a 3D model. So as I told you, I have already imported a 3D model, which is a windmill. So I will import this GLTF windmill, and obviously it's too small. So what I will do, actually it's too big. So what I will do, I will click it and scale it to appropriate size so that you can see actually how does it look like. All right, and I might have to zoom a little bit because it's still not visible. So I will zoom it, and now you can see that windmill that we are going to use for powering the factory, the cookie factory. But this windmill doesn't look like a real windmill. It's very dark here. So let's bring some light into the action. So what I will do from the settings, I will actually set up the environmental preset and make it neutral. I could also use a 3D light on this device, but again, if you have a lot of 3D graphics, you do not want to put light on each one of them. You want to use this global preset so that you can create lights for the entire environment. All right, so what's next? I mean, we have already created a 3D model. So what I will do, I will attach a model shader, right, with this 3D model. So I could attach a tag. For example, tag could be a speed. It could be, I can have multiple tags to a 3D graphics model. It could be how many RPMs are going on, and we can also attach model shader so that we can change the color of certain models based on some parameters, some threshold. So let's see that in action. So I will add a model shader, and I will attach the entity. This is how you bring data together with the 3D model. So what I will do, the entity we created earlier, that windmill 001, I will attach it to this windmill. And I'm interested in the speed property, which is, by the way, the only property we have data coming in through. And what I will do, I will also attach a rule together with this so that we can represent this shader in multiple colors based on the speed of wind. So what I have done, I went ahead and actually changed these different expressions. For example, if speed is less than 100, I want to make sure this shader shows the red color. Similarly, if the speed is greater than or equal to 100, I want to show the color in different color, show this shader in different color. For example, in this case, I choose the green color. So that means speed of wind is good enough and we are getting good electricity. All right. Other than that, we can also create virtual cameras that are pointing to certain devices. And we can have virtual camera, let's say, in every room of the factory or a building, so that operators can reach directly to that place very quickly. They don't have to actually scroll and navigate around the 3D environment. So you can have a lot of different cameras pointing to different devices or equipments. All right, so after adding the camera, now you can see the camera is also in the scene. Now what I will do, I have already created a Grafana workspace. So I will navigate to the Grafana, and there you can see in a minute that I have already created a workspace. And by the way, for this workspace, I have already set up all the permissions so that I can access to TwinMaker data and the other way around, because the application is in the Grafana dashboard. So here you can see what I'm doing now. I will create a new dashboard, add a new panel, and I can add different panels. For example, in this particular scene, you are seeing that time series panel is coming up. And from the query, I will select a history by entity. And I'm selecting all that entities that I have created, like windmill, and component name is windmill metrics. So now you can see the data that is the mock data that is coming to this particular through this particular windmill is mapped to this time series. All right, so I will apply it, but this is not enough. We want to see this in graphics in a 3D way, right? Like just having these line charts is not enough. So what I will do, for my operators, plant operators, I will add IoT TwinMaker scene viewer panel, and we will name it like wind farm, and in the same way, I will associate it with the wind farm scene that is coming through the IoT TwinMaker, and you will be able to see this scene live on the screen. So what I did, I selected the same properties, and now you can see this windmill is in green color. Can you tell me why this windmill is in green color? Because the data is, the speed of the wind is more than 100. So if the speed of the wind is going down below 100, the color should change to something else. And it changed to red. All right, that's it for the demo. I will switch back to the PowerPoint. So you can deploy this cookie factory demo in your account today. Just follow this GitHub link for more instructions. Enough with the fictitious factory. Let's talk about a real factory now. To tell us more about Northvolt's approach to sustainable manufacturing, I want to invite Marcus. But first, let's watch this inspiring video footage that introduces the Northvolt's vision.
The demand for electrification and the demand for lithium-ion batteries is growing so fast that we're going to need to scale production at a really incredible pace.
We're building one of the largest battery plants in Europe.
Next step is beyond building more batteries, it's also building greener batteries.
Recycling, bringing as much of the capacity back.
Those batteries are then becoming new raw materials for next generation of battery production.
We already had a world-class team.
It's focusing on investing into a sustainable future, building a fully circular economy.
Thank you, Sajid. My name is Marcus Ulmefors, and I work with the data platform for Northvolt Factories. I'm delighted to share our story with you all here today. Before talking about scaling the digital factories for battery manufacturing, I want to cover some background and set the scene a bit. We begin with the global sales of electric vehicles. So in 2022, the first half of 2022, the global market share reached over 9%. This is excluding hybrids, fully electric only. Now, let's use the same numbers, but with one additional feature. Mapping on the right here, we have the global total manufacturing capacity of lithium-ion batteries. So to support 6% of global electric vehicle market share, in 2021, the production of lithium-ion batteries was 300 gigawatt hours. So how much is a gigawatt hour? That's enough to build 15,000 electric vehicles, and fully charged, that electrical energy is enough to drive 6 million kilometers. That's 150 laps around the equator. Now, so let's make a little prediction towards the future, extending this to 2030. So who believes with this development that we'll need over 1,000 gigawatt hours per year by 2030? Okay, great. How about more than 2,000? Right? It turns out we need even more. So industry experts normally talk about numbers exceeding 4,000. That's 10x 2021. And lots of experts actually state numbers that are around 6,000. So that's literally off the charts in this visualization. Now, assuming that a large gigafactory has a capacity of 30 gigawatt hours, that means more than 100 gigafactories before the end of the decade. What drives these numbers? So far, I talked about electric vehicles. That's an obvious, visible example. But we will need electrification and lithium-ion batteries also for energy storage on the grid and for powering buses, trucks, boats, ferries, and even commercial passenger flight before the end of this decade. So to make enough batteries and factories to meet this demand, we will have a race against the clock. Welcome to Skellefteå. This is an 8-hour drive north of Stockholm, the capital of Sweden. This is the site for Northvolt's first gigafactory. The factory is called Ett, which is Swedish for one. Fully built out, this will have enough capacity to power 1 million electric vehicles per year. And where do we stand today? The buildings you see in this image represent 1/4 of the fully planned capacity. In December 2021, we assembled our first battery cell, and in 2022, we made our first customer deliveries. This is real, now, and it's just the beginning. So what's special about Northvolt and this factory? Let's start with energy. This location is chosen deliberately for access to 100% renewable energy from nearby rivers and wind. It's also a manifestation for the strategic investment in vertical integration. The obvious one is the cell production that we know, but before that, we also make our own battery chemistry for the electrode. That is called the active material. In other Northvolt sites, we design, manufacture, and operate battery packs or systems. And by end of life, battery packs are essentially high-grade ore, and that is perfect for recycling. For that reason, we are building already a giga-scale recycling plant at the very same site. And the output of this recycling process feeds back into the active material manufacturing. So now we are basically closing the loop with this co-location. So closing the loop of circular manufacturing, and we replace the standard global supply chain with a 5-minute walk. Vertical integration is great for sustainability, and it also opens the door for flexible data sharing between links in the value chain. That enables more sophisticated modeling and deeper insight. Imagine not only making the world's greenest batteries, but also the world's smartest. How would you go about that? Let's dive into the technical architecture. So now, before we talk about scale, we're going to cover 3 aspects of the technical architecture, starting with monitoring, and then controls, and the data platform. We'll start with talking about the data sources and fundamental monitoring. In a manufacturing setting, we interact with equipment that isn't designed to communicate over the internet. Very often, our data source is a PLC, which specializes in controlling mechanical equipment. Our environment starts way at the left with the IoT gateway, which is an edge computer running our own Yocto-based Linux distribution. Running on that gateway, we have the Mapper software, which provides an abstraction for the equipment that helps us reduce complexity in our cloud environment. The Mapper collects data over one of our supported methods and protocols, for example, OPC UA, HTTP REST, or SQL. Going down to the bottom row, you see how we use IoT Core to generate certificates so that we can authenticate to the correct account and start streaming data into the Kinesis data streams. I've now so far talked about this IoT gateway and mapper as a computer running some software. In reality, this IoT platform runs on K3s. And K3s is a lightweight Kubernetes distribution that is specifically designed for these IoT production workloads. The physical IoT gateways are the worker nodes in the factory, and the control plane runs in the cloud in our AWS account. The mapper software is deployed as highly available pods running on a pair of IoT gateways. Fully built out, a typical factory will have thousands of these gateways collecting data from millions of data points. The actual hardware can range from a small Raspberry Pi-like device for light monitoring to more powerful machines with onboard GPUs to run inference of machine learning models at large data sets, for example, images. Managing software running on thousands of devices requires reusability and flexibility and customization. So we have a main repository where every release is tagged with its specific destination. Once reviewed code is merged, Rancher Fleet deploys the corresponding Helm charts to the K3s cluster. Pods with the tag released will now start in the right gateways, communicating with the right manufacturing equipment. Within monitoring, broadly, we want to solve 3 use cases. The first is near real-time monitoring for raising alerts and making fast decisions. Second, we want to do investigation analytics on larger data sets, maybe high-resolution data that was collected a long time ago. And third, we want to join this data with contextual data within traceability to make flexible joins and enhance, for example, event data and long-running processes. So that is the middle row that runs on Kinesis, Lambda, RDS, PostgreSQL, and visualized in tools such as Grafana. For investigations and analytics, we use the top row here, where we repartition raw data and store as optimized Parquet files so that we can serve through Athena for larger queries. We can also perform the joins with contextual data for the same time window using Redshift. Monitoring is the first step. It's a crucial step. And now let's go further and start interact with the factory. Also running here in a cloud environment is software that controls critical features and functions of our manufacturing line. We'll start with the bottom right corner with the business systems, ERP and PLM. ERP, or Enterprise Resource Planning, is where you have central management of company assets like cash and inventory. It's also where you'll see transactions for purchase orders, production orders, and sales orders. PLM, product lifecycle management, is the definition of a product, for example, a battery cell of a specific model. This is also the source of truth for quality tolerances, product design, and the manufacturing processes. So now let's consider an example where these systems all interact. It starts with ERP releasing a production order, and now a battery cell moves towards the next manufacturing step, let's say an X-ray machine. Images are taken and then analyzed with computer vision algorithms to produce an event with a result. Our mapper software now grabs that data and streams it up to Kinesis. Using production order information and the event data, we can go to PLM and request the corresponding quality control plan for this process, for this battery cell. Now we can validate that every single critical measurement is within defined tolerances. This whole procedure runs serverless in Kinesis, Lambda, and DynamoDB. Ramping a gigafactory is extremely exciting, but let's say it's not always smooth sailing. So what happens when something doesn't really go according to plan? For example, if a measurement is outside of the tolerances, a nonconformity alert is raised and saved in the traceability document of the battery cell. The quality team now has the mandate to decide whether or not to scrap the cell or if it's released further. This decision is recorded in the top right, where you see the purpose-built web and mobile apps. These communicate with our backend through the GraphQL endpoint. Now, what happens if a non-conformant material proceeds in the manufacturing line? Well, the equipment will know the material ID, so we can ask a cloud service through the API gateway in the bottom left whether or not further processing is allowed. If the response is negative, the operations will halt. Every interruption and quality deviation is captured and recorded in near real time. And instant access to this data allows us to course correct right away on the manufacturing line. In this architecture, you see 4 lambdas. In reality, these are communication and integration patterns, and since we run many applications in parallel, there are quite a few more instances of them. So for a section of the factory, how many lambdas do you think we'll have here? Maybe 20? Maybe 40? Today, there are more than 100. So here you have some examples of how cloud software uses data in near real time to automate and control our manufacturing processes. Of course, we also take a copy of this data, store it, refine it to drive analytics. And for that, we'll take a closer look at the data platform. Data is strategic at Northvolt. It starts with traceability, which essentially allows us to track exactly what happens to every single cell component in every manufacturing process. High-resolution data from factories and labs constitute a unique asset that we can use for optimizing operations and for developing better products. Within each factory, we'll have thousands of gateways with hundreds of thousands of data records per second. So we need a flexible and scalable data platform that can provide us with the technology we need for monitoring, analytics, data science, and machine learning. We manage hundreds of data sets in the data platform today. And here we're going to look at 3 categories of data flows that are specifically designed to power analytics and for data-driven operations. Let's start with the center row. That's where we have contextual data. This data comes from the manufacturing line, from equipment, or from software applications running in the cloud, with or without a human in the loop. This can be immutable event streams or mutable data, such as states or identities. Every write operation to DynamoDB is consumed through change data capture for DynamoDB streams. We then take these hundreds of data sets and filter and map them, and then join with other data sets to create these specifically designed data sets for analytics. The analytics data sets are then used by technicians, engineers, and managers to prioritize initiatives, track progress, and report on results. We use an ELT pattern with extract to S3, load into Redshift, and transform within Redshift using dbt. Everything orchestrated using Airflow. The bottom row represents electrical measurements, so from ready cells in a lab. This is time series data with high resolution and long duration, can be many months. And we use this data to do performance analysis and to perform product R&D. In the top row, we upload images and other large files directly to S3. This can be, for example, photos or camera images from the manufacturing line that allows us to train machine learning models for vision-based defect detection systems. We then use distributed training with multiple cloud GPUs and deploy the most performant models onto the IoT gateways with onboard GPUs for inference on the manufacturing line. So those are our fundamental features of the architecture that we run in AWS. That's great, so let's go on to scaling. Greenfield factories have no existing legacy. That allows us to use cloud-native and serverless strategy. How do we design this? What are our principles? The gigafactories are huge investments, billions of dollars. That means every single minute of downtime is very expensive. So using cloud-native technologies allows us to increase reliability. We achieve security by compartmentalization and zero trust across our cloud architecture. We choose appropriate separation granularity to decrease blast radius. And then to scale quickly, we use many excellent services provided by AWS for network and compute and storage, but we also need to manage the complexity of a growing system. So there we need to be able to combine and balance the global reusability with site-specific optimizations. To scale a digital blueprint, we need it to be modular, a single concept across factories, without sacrificing the ability to create optimizations for a specific factory or area. And Northvolt's vision and mission is to create the world's greenest battery. So using AWS, we can use optimized technologies for the cloud, and not least flexible utilization of shared resources, for example, using serverless. On top of that, the Stockholm EU North 1 region runs on 100% renewable energy, which fits our mission perfectly. With a high-quality platform, reliability and development speed can coexist. So from a software release perspective, our factory shouldn't be different from a flexible web app, meaning we should support blue-green deployments and canary deployments. Taking all these into account, where do we end up? So introducing Northvolt Cloud Factory Modules. We start with a physical layout of a factory. We then create a dedicated building account to start deploying the K3S cluster with hundreds of IoT gateways. And here's where the mappers authenticate to the right building account and start ingesting streaming data into Kinesis data streams. This is also where the backend lambdas will run that we looked at before. In the core account, we use functionality for features that need to be shared across buildings. For example, DynamoDB for operational transactional data, but also RDS instances, Elastic Kubernetes service, OpenSearch, and raw data in S3. The data account is where we refine data into analytics data sets. We'll find here Redshift and Airflow and dbt, but also the MLOps platform. You can think of this entire account as a DAG, with data being replayable from source, and also where data in general doesn't flow backwards. So that wraps up the factory-specific accounts. What do we need more than this? In fact, it turns out that we need a little bit of help across the entire ecosystem. For example, the share account. This is where we run features that help development and operations. We manage secrets, Elastic Container Registry, and our observability platform. For example, OpenSearch service, Prometheus, and Grafana. Network. The networking backbone has transit gateways, firewalls, and direct connect. This connects not only our physical sites, but also controls the incoming and outgoing data between our AWS accounts. And this account also provides the integration with other cloud providers, who shall remain unnamed today. And in the global account, we have a central GraphQL endpoint, providing like consistent front-end user experience for our applications. The backend is accessed through a factory-specific federated endpoint running in the core account. This enables access control through user roles and location. All right, now we have our first factory. Are we done? No, we scale. We need more factories. So let's add one more. And here we create the same integrations for in the global accounts, and we add the core and data platform. The real strength of the concept is visible in the building accounts, because here, depending on the geographical location and the product that we make, we'll need different processes and therefore different building types. With the Cloud Factory modules, we can represent these differences without changing our concept. This remains consistent. All right, so where does that take us? To achieve reliability and optimized performance at scale, we need excellent tooling for infrastructure as code. As technology moves towards everything as code, what becomes our vision? You probably guessed it by now. Factory as code. Why not something like this? The world will need hundreds of new battery factories for us to transition to a cleaner energy future. At Northvolt, this is real now, and we're just getting started. Thank you so much for listening to our story today. I hope you will remain with us for the exciting future, maybe already on Wednesday or Thursday in one of the deep dive chalk talks with my colleagues. With that, I want to welcome Sajid back on stage, and thank you so much.
Thank you, Marcus. We are committed to support Northvolt in their efforts to decarbonize the energy for a greener future. This is the perfect time to grab your phone camera and take a picture of this and some of the following slides. You can use these resources to learn more. And you can also read more about the Connected Factory module in Northvolt's blog post. And if your schedule is not fully booked, here are some of the sessions you should attend. You might already have some of these sessions in your schedule. And if you have time and interest in creating digital twins of aerospace use cases, then please check out IoT TwinMaker workshop, 1 p.m. today at Caesars Forum. Similarly, don't forget to attend the Chalk Talk with Northvolt on Wednesday, 12:15 p.m. in Caesars Forum. Let me ask you one more time. Raise your hands if you're responsible for sustainability in your company. All right, so in the end, I will leave you with this quote from Jeff Bezos that says, "We must conserve what we still have, we must restore what we have lost, and we must grow what we need to live without degrading the planet for future generations." It was a pleasure presenting in front of you today. Please don't be the tab sunduku like me, and don't forget to complete the session survey. Thank you very much.